Hello everyone, my name is Darya and I'm a chief scientist in Vista Clara. Today I'm going to talk about in-situ NMR measurements to quantify crude oil at National Crude Oil Spilled Fate and Natural Alternation Research Site in Pinewood, Minnesota. Hydrocarbon contamination in groundwater is an ubiquitous problem worldwide, and this contamination can happen due to surface spills, pipeline ruptures, underground tank leakages, and it can be found in the formation in the form of non-aqueous phase liquid or dissolved phase. And it's crucial and very important to characterize and also quantify hydrocarbons in the formation for many reasons, such as proper planning of the remediation actions in the facility. So traditional approaches to characterize hydrocarbons in the formation based on sample coring and fluid sampling. However, for example, SAM coring can provide formation disturbance, and these methods provide only smeared spatial and temporal response. It can be very costly in case you need to collect multiple samples to monitor your remediation and send the samples to the lab for direct quantification of the hydrocarbons in these samples, and it can be very costly. And in the end of this process, you also need to deal with investigation-derived waste disposal. So several in-situ methods exist today to characterize hydrocarbons, and among them is the Direct Push Member Interface Probe, or MEP, which can detect VOCs that can penetrate to the probe through the semi-permeable membrane, and also Direct Push Optical Image Profiler, or RAP, tool that uses real-time analysis of fluorescence images to detect the non-aqueous phase hydrocarbons. So these methods are great, however, they're not very quantitative. So the focus of my talk today will be on additional in-situ method which can be very useful to quantify hydrocarbons in the formation, and this method is called nuclear magnetic resonance, or NMR. So NMR is a very powerful technique which is used in many disciplines such as organic chemistry and biology, and also in medicine. The method is also used in oil and gas industry and groundwater investigations. So NMR logging tool has permanent magnets. The measurement itself is done in the presence of the strong magnetic field, and it also has transmit and received coils in the vicinity of these magnets. And basically the magnets of the NMR tools cause the polarization of the hydrogens in the formation, and inductance coils are used in order to excite the polarized spins from their equilibrium state, which is parallel to the main magnetic field. Basically excite the hydrogens from that equilibrium, and after that excitation pulse is turned off, the receive coils are used to detect the decaying NMR signal. So since the NMR borehole logging tools use permanent magnets, the magnetic field is not uniform, and you will have a decrease in magnetic field as you move far away from the sensor. And in this case, stronger magnetic field which are associated with higher NMR frequencies can be found closer to the tool, and weaker magnetic fields which are associated with lower NMR frequencies can be found at some distance from the probe. And also a very important characteristic of these tools, since we have that decaying magnetic field as a distance from the sensor, it will also have a magnetic field gradient. So here on the right you can see the the illustration of the NMR tool. So NMR tool directly measures the hydrogen in the formation fluids within the formation. So this green shell shows the zones of investigation. So these zones are tuned in the way that they are focused directly within the formation, outside of the zone of disturbance from the drilling. The most common sequence that is used to measure water signal in the formation is by NMR is called CPMG, and this is just a set of radio frequency pulses that we applied in order to measure our NMR signal. So the first pulse is the excitation pulse, is the 90 degrees pulse that we need to apply in order to excite the hydrogens from their equilibrium state, which is parallel to the magnetic field. And after that, we have a series of 180 degrees pulses, which basically we use them in order to refocus that magnetization on the transverse plane, and we measure our signal in between each 180 degree pulse at the maximum of the echo. So in the end, we will have NMR signal as a function of the time, and this signal will have a multi-exponential decay because we don't really have uniform pores in the formation. And we can use the signal decay and feed it to multi-exponential function in order to estimate the distribution of T2 relaxation times, that it's very useful to differentiate between water in large pores and water in small pores, because the relaxation of water in the large pores will have very long relaxation time, and the relaxation of water in the small pores will have very short relaxation time. So we can use sort of cutoffs to differentiate between different populations of the water. However, what happens if we use that sequence in multi-fluid system? So let's imagine we have water and oil, and these two fluids have different relaxation properties. So yeah, we can say that everything we detect with the smaller T2 relaxation times is basically the signal of oil, and yeah, so well, we can clearly then differentiate between them. However, in many cases it's not happening, because water in the very small pores, like water in clay, will also have very short relaxation times, very similar to the relaxation times of NAPL. So this method is not very reliable. But in more common cases, the fluids, different types of fluids will just overlap and will have very similar T2 relaxation properties. Like in this case, so we can't really, it's not possible to differentiate between different fluid types based on the CPMG pulse sequence. So what can we do? How we still can differentiate between different type of fluids with NMR? So in this case, we can use a different experiment, and this experiment is called diffusion NMR. And this is a very common experiment which is done to separate fluids based on their diffusivity. And as all of us know, diffusivity is a function of viscosity. So very long viscous hydrocarbon chains found in crude oil will have very slow diffusivity as compared to water. So by conducting that experiment, we can basically differentiate between these different fluid types, and the measurement can be conducted only in the presence of the strong magnetic field, and all NMR borehole logging tools do have a strong magnetic field, because the change in magnetic, because we don't have a uniform magnetic field in these probes, we use permanent magnets. And in order to properly differentiate between different fluid types, we need to repeat this experiment with different diffusion times. So here in the bottom you can see the diffusion NMR pulse sequence, and this is just additional delay that we add in the beginning of the standard CPMG pulse sequence. So we just repeat that experiment with different diffusion times. So here, just to show you the laboratory experimental results that we detect with diffusion NMR pulse sequence. So the first example is just the sand saturated with the bulk water. And diffusion NMR experiments were conducted with different diffusion times. You can see that the signal has a very long decay, which is kind of expected due to the relatively large pores of the sand. And you can also see that as we increase diffusion time, the initial signal amplitude is decreasing accordingly. This is expected because we have that diffusion delay between the actual CPMG pulse sequence. So if we take all the data set, all these signal decays that were obtained with different diffusion times and properly analyze it, we can estimate diffusion to correlation map. And in this case, since we have only one fluid type in the formation, which is water, we detect only single peak. And this single peak will have a very known diffusion coefficient of water at room temperature, which is about 2 micrometers square per millisecond. And it also will have a long T2 relaxation time of about 1 second. In case we have a system of soil saturated with 50% water, 50% oil, we of course see that the signal decay changes quite a bit as we increase our diffusion time. However, then we analyze that experiment, we can see that in addition to the water peak, which appears at the same location and has the same diffusion coefficient of about 2 micrometers square per millisecond, we start seeing additional peaks, which are oil peaks, and these peaks will have smaller diffusion coefficient as compared to that of the water. However, some of them will have very similar relaxation, T2 relaxation, as that of water. Therefore, if we were using standard CPMG pulse sequence to try to differentiate between different fluid types, we couldn't really reliably do that in this case. So here just another example that the sand was saturated with 80% water and 20% oil, and we still have these 3 peaks of oil, but their amplitude is just smaller because the concentration of oil in this sample is smaller. So the focus of my talk today will be on diffusion NMR investigation at National Crude Oil Spill Fate and Natural Detonation Research Site in Pinewood, Minnesota, and to many of you this site is known as Bemidji Crude Oil Spill Fate Site. So this study was done in collaboration with the Geoprobe, and the investigation was conducted at the sough plume area. And here on the right you can see the map of this site, and in green you can see the locations of the different monitoring wells at this site, and symbols in orange present the location for OAP and NMR measurements. So initial logs were conducted with OAP-UV and OAP-G probes to identify the presence of NAPL and select locations for the direct push NMR investigations. And OAP was combined with the HPT, and as we were done with the OAP, we conducted direct push NMR measurements at the same location. So here on the right you can find a brief illustration of the direct push NMR deployment. So in order to use that tool, we first deploy empty 2¼ inch rods to desired depth, and then we use 1.4 inch ID NMR probe and deploy that probe through these rods using extendable push rods. And after we did that, the drill rods are retracted using the direct push ring, and we use the extendable push rods to hold the probe in place. So once the probe is deployed, the NMR measurements are conducted on the way up using step mode, and the vertical resolution of this probe is 6 inches. So in this study we first conducted CPMG, standard CPMG experiment along entire log to estimate total water content, relative precise distribution, and hydraulic conductivity, and then we conducted diffusion NMR measurements at several locations along each log due to limited time. So here are the results of the first location. So OAP could detect NAPL very nicely, both above and below water table, which is about 8 feet. And in this case, it seems like the OAP-G looked better than OAP-UV. So after we were done with the OAP, we conducted direct push NMR at the same location. So we were able to detect very nice signal, very low noise signal, and very a lot of mobile water content below 12 feet, but it's not very much clear what's going on here above water table. From using that log, we can't really tell if there's any NAPL. And by the way, the location of this log is selected here in this map in the bottom right corner. So after doing that, we conducted diffusion NMR along this log at 6 different locations, and these locations are selected here with the red lines. So here, just to show you diffusion to correlation maps that we obtained in that first location within the sough plume. And we use these diffusion to correlation maps to basically differentiate and quantify fluid types in the formation. And just to remind you that diffusion coefficient of water is expected to be significantly higher than that of the crude oil. And we can set sort of a threshold line and define all the signals above that threshold line with higher diffusion coefficient to be related to the water signal, to water signals or to aqueous zone, and all signals below that line with lower diffusion coefficient are defined as a non-aqueous zone and basically related to the crude oil signals in the formation. So based on these correlation maps that I showed you in the previous slide, we can estimate the crude oil content directly within the formation. And here on this slide, the crude oil content is shown as a red crosses. And this the crude oil content basically plotted together with the total water content in estimated from the CPMG experiment. And if we convert that crude oil content to the concentration, so here on the right you can see the crude oil concentration that we estimated, and it looks like it's between 5 to 10 feet. It's a lot of crude oil. It's more than 45%, and here at 10 feet it reaches like 70% crude oil was detected. And as we go deeper, no crude oil is detected, as you can see here. So it's just water. So here is the second location within the sough plume that we used to collect OAP and NMR data. So again, OAP could detect crude oil very nicely. Again, OAPG was performing better at this site. We could detect crude oil both above and below water table, which is about 6 feet in this location. And again, the standard CPMG pulse sequence provided nice results, but we unfortunately can't tell from this if we have any crude oil. So we conducted a lot of diffusion NMR experiments at this location, and the results of the crude oil content are plotted as a red crosses in this middle plot and overlaid with the water content plot. So you can still see that it's a lot of crude oil at between 3 to 8 feet. And if you convert it to the crude oil concentration, we can see that at 5 feet is about 55% crude oil. So that's quite a bit. And here's an example of the data we collected outside of the sough plume. So the location is selected here as a red cross, and OAP couldn't detect any signal from the NAPL, from the hydrocarbons. And actually diffusion NMR could detect some crude oil around 3 feet. So if you look on this diffusion to correlation maps, you can actually see that yes, in this location is that peak with lower diffusion coefficient than that of water, and that peak corresponds to 55% crude oil concentration in this location. But if you look a deeper location at about 10 feet, you can see that it's mostly it's just water. It's a water peak. So just to conclude this study, so this study showed a good correlation between OIP and NMR measurements. OIP could detect and locate crude oil based on the fluorescence emitted from the hydrocarbons, and diffusion NMR represents a promising method for direct quantification of crude oil content directly within the formation. And here it's very important to mention that diffusion NMR can be used with all borehole logging NMR tools, because all of these tools have a strong magnetic field gradient, and so measure NAPL content in already existing monitoring wells directly within the formation. So the main limitation of the diffusion-based NMR is that the current acquisition protocol requires long acquisition times. We need to repeat the diffusion NMR experiment with multiple diffusion times in order to more accurately differentiate between different types of fluids in the formation. And currently the measurement is done only at stationary locations, and continuous log is currently unavailable, but we hope that in the near future it will be changed, it will be modified. Thank you very much for your attention, and I would like to thank Jared Trost from USGS for his help with the field work, and also to thank US Department of Energy for funding this work.